Hey guys, welcome back. And right now we're going to take a look at the continuation of the ultimate guide to the electric field. If you haven't seen part one, in part one I go over the conceptual side, which is the more difficult side, telling what voltage means, what electric field means, and things like that. In this section, which is again a continuation of that, we're going to take a look at the quantitative side. So we're going to answer the question, now we know which direction these charges push each other. Exactly how many newtons of force is going on there, or equivalently, before we figure out which direction the electric field pointed, exactly how many newtons per coulomb is it? That's what this lesson is going to cover. Okay, so really there's only going to be 4 equations that I'll go over today, and one of them is pretty trivial. Before that, I just want to go over a number you should know. So since we were doing so much conceptual, I didn't really tell you much about units and things. So one quick note is that charge is measured in coulombs. That's the unit of charge. And 1 coulomb is an absolutely astronomical amount of charge. The charge to remember that you will use a ton is that the charge of an electron is 1.6 times 10 to the negative 19th coulombs. And it is negative. Similarly, the proton charge, which is the opposite, is just positive 1.6 times 10 to the negative 19th coulombs. So you actually need you actually need 10 to the 20th, which is, I don't know, quadrillions, quintillions of electrons in order to have 1 coulomb of charge. Typical problems will involve things generally like microcoulombs. That's 10 to the negative 6th coulombs. A microcoulomb is a very small unit of charge. And that will usually give you forces of size that you expect. Okay. With that, I think we can go straight into the first equation, and it's going to be Coulomb's law, which told us how hard, so how much force, of repulsion or attraction between 2 charges. And we already know from our general abilities from last time, just looking at it, what direction things will get pushed. The exact numerical amount is told to us by this number. K is just a constant. It's 9 times 10 to the 9th. It's also sometimes written 1 over 4 pi epsilon 0, where epsilon 0 is a different constant, and these 2 expressions are the same number. And it's called Coulomb's constant. So the force is K times the charge of object 1 times the charge of object 2 divided by the distance between them squared. And if you want to, if you need to specify the direction of the force push, the push on each object is, well, at least if Q1 and Q2 are positive, R hat is away from the creator. And again, this would be if you're asked what the force on, let's call this one charge 1, charge 2. If you're asking what is the force on charge 2, you can obviously calculate the size. That's just this expression. If I tell you what Q1, Q2, and R are, you can obviously calculate the size of it, and charge 2 is going to feel a push away from the thing creating the push on it. So the push will be away from charge 1. And conversely, if you're trying to figure out what is the force on charge 1 due to the created field of charge 2, it points away from the creator by default if they're both positive. Now, automatically, if one of the charges is negative, then it tells you that the force, let's pretend we're looking at the force felt by charge 2, and let's make charge 2 negative. Well, r hat away from the creator of 1 still points this way, but when you compute this number, you'll get like negative 20 newtons. So if things this direction are positive 2 r hat and positive 20 r hat, if arrows like that point to the right, then your answer of negative 20 r hat will be an arrow directed to the left. So this automatically encodes attraction or repulsion. But you should also check by hand after if you've gotten the right number, or not the right number, if you've gotten the push in the right direction. So for instance, it's very easy sometimes to forget r hat points away from the creator and not towards the creator, and you'll sometimes flip a sign, and if you're looking afterwards at your answer and you say, hey, my arrow is pointing this way, but looking at the situation, I know my answer should be that way. Let me see if I messed up a minus sign somewhere. So it gives you an extra safety net, and it's really important in these problems to get it. So I'll put, but you should always check with your intuition if the answer makes sense. Okay, let's do an example here. Let's say we have charge 1 will be of size 2 microcoulombs. Charge 2 will be of size negative 4 microcoulombs. And the separation between them, let me just pull up something. Let's say they are separated by a distance of 9 centimeters. A question might be, find the force on charge 2 due to charge 1. Okay, so first it might be good to check what direction we expect our result to go in. So this is a positive charge, this is a negative charge. We expect charge 2 to get pulled that way towards charge 1. Okay, Coulomb's law will tell us the size of the force. It's k q1 q2 over r squared. And really all we have to do is convert microcoulombs to coulombs, centimeters to meters, and then we'll be done. So k is 9 times 10 to the 9th. Q1, now again, microcoulombs is 10 to the negative 6th coulombs. And I'm going to skip writing units here. Q2 is negative 4, and again, each microcoulomb is 10 to the negative 6th coulombs, divided by 9 centimeters, so 9 1/100ths of a meter is 0.09 meters squared. Alternatively, if you want, you can write centimeters, and this might actually be more helpful. 9 times 10 to the negative 2 meters squared. That way we can use our scientific notation tricks to deal with all these powers of 10. So if we group a bunch of crap together, let's see, upstairs we have 9 times 2 times negative 4, and then all the powers of 10. Let's see, we have 10 to the 9th, 10 to the negative 6th, and again 10 to the negative 6th. Downstairs we have 9 squared and 10 to the negative 2 squared. By the way, at this point, if you do have your calculator, you can go straight from this to the answer. But as an example, if you do it by hand, you can simplify some of the exponents. So let's see, we have 10 to the negative 4th downstairs, which is the same as 10 to the positive 4th upstairs. And now we have 13 powers of 10 minus 12 powers of 10, so all this actually just combines down to 10. The 9s cancel, So we have negative 80 over 9 as our answer. And again, hidden in this is the direction away from the creator. So positive numbers would indicate along this direction, but we have gotten a negative number. So negative 80 over 9th is the same thing, or negative 80 over 9 newtons is the same thing as saying 80 over 9 newtons directed to the left, which is what we expected, right? We wanted an attractive force, and we just double checked that we got our minus signs right. So here is the answer for the force. Okay, next thing I'm going to tell you, and by the way, I could do another example with these problems. The next example I would give is charge 1 here, charge 2 here, and charge 3 here, and I tell you what size they are, and the question would be find magnitude and direction of the force on charge 3. Now, should I actually do this? Yeah, you know what? Let's do this. Okay. For ease of computation. Okay, for ease of computation, what I'll do is I'll have us reuse these numbers at first. So I'll have a 2 microcoulomb, and Q3 will be a negative 4 microcoulomb. Q2 will make it 6 microcoulombs. And we're going to make this distance, again, this is just to make sure we don't have to do another whole long calculation for no reason. We'll make this distance between these two guys 9 centimeters, and we'll make this 3 centimeters. Okay, so let's find the magnitude and the direction of the force on charge 3. So it's going to just be the sum of the forces due to charge 1 and charge 2. And now, vaguely, we expect that the pull of Q1 on Q3 will cause a pull this way, and the repulsion of Q3, or sorry, no, this will be an attraction too, because, right, Q3 is negative, Q2 is positive. So the attractive force from Q3 and Q2 will point this way. So generally, we expect we're going to get an arrow something like that one that I just sketched. But all we're going to do is find these two individual forces and then add them up like vectors and find the hypotenuse and such. Okay. So between charge 1 and 3, you do the same thing that we just did. You find the force by using k q1 q2 over r squared. And we just computed that this force is 80 over 9. Oops, I can't scroll. 80 over 9 to the left. So we found this net force already. Now let's find the force from charge 2 on charge 3. Okay. Again, we're just going to use Coulomb's law. Let's see. We have 9 times 10 to the 9th as usual from K. The first charge involved, we'll call it charge 2 is the first one involved, is 6 microcoulombs. Again, Q1 and Q2, they aren't of charge 1 and charge 2, they're of the two objects that you're calculating the force between. So Q1, I'm using this guy, so 6 microcoulombs, and Q2, I'll use the other guy involved in the pull, so Q3. Divided by the distance squared, and again, the distance is in centimeters, so we need to convert it. And at this point, I will punch this into my calculator. Let's see, 9E9 times 6E negative 6 times negative 4E negative 6 divided by, remember to close your parentheses if you're doing division by scientific notation, and the result is negative 240. Now, again, just to comment on the sign, the default for a positive answer would be away from the creator of the push, but we got a negative answer, so as we expected, it is an attractive force pulling down of size 240 newtons. So now all we have left to do is we have a leftwards pull of, let me see what 80 over 9 is, 8.9. So we have an 8.9 pull to the left and a negative 240 pull downwards. And our goal is to find the size of the pull, so this hypotenuse, and either this angle or we can later add 180 to it to get the total angle from the x-axis. So first, to find the magnitude, we're going to use the Pythagorean theorem. So square root, and by the way, sorry, I shouldn't have written negative 240. It's 240. We know it's directed down, so all of our answers will be, we're doing manipulations on the side lengths of a triangle, and then we understand what direction the triangle is from the way I drew it, right? If I drew it like this, and this being 240 and this being 8.9, that would be a force pointing in a different direction. So Pythagorean theorem says you take the square root of 8.9 squared plus 240 squared, and you get 240.2 newtons. That is the magnitude of the force. Again, you don't add these two together. You have to do the Pythagorean theorem to find their hypotenuse length. And then we're after this angle right here. Now, remember from trig, if you're hunting after an angle, by the way, I do have a video on trig up if anyone wants a refresher. If you're hunting after the size of this angle, and you're told the side opposite and adjacent to it, this formula, which relates the angle to how big the sides next to it are, this formula looks pretty promising, right? This is the side opposite, this is the adjacent, and all you have to do is take the arc tangent of both sides. Now, if you didn't watch the trig video, I just want to point out again, this is not cotangent, and it's also not 1 divided by the tangent of something. It's its own button on your calculator, sometimes called arctan. If you do it on like Wolfram Alpha, the arctan will show up. So you take the arctan of both sides, and you get that theta equals arctan of 240 divided by 8.9 is 87.9. So our final picture is we have this arrow pointing diagonally downwards of size 240.2 newtons, and this angle right here is 87.9 degrees. So it's not 87.9 above that way, it's 87.9 degrees below left, or if you're using map directions, south of west. Alternatively, your teacher might tell you what's its angle relative to the positive x-axis. In that case, the angle of this arrow is 180 degrees plus the 87.9 degrees. But this, in one way or another, constitutes a complete answer to the problem. All right, next we're going to do electric field. So electric field is almost identical to the calculation we just did. The only difference is that there's only one Q upstairs. Okay, and the Q is, I'm going to write a little subscript because this is where people can get confused. It's the Q of the thing creating the electric field. Okay, and if you want to specify the direction of the electric field, it's again in the direction away from the creator. So, as a quick example, if we're asked what is the electric field 2 centimeters away from a proton, and this is going to be a crazy number, remember, because the charge in coulombs of a proton is ridiculously small. The electric field is going to be computed as K as usual. The charge of a proton, remember, is this number 1.6 times 10 to the negative 19th coulombs. And then we divide it by the distance squared. Now I need to plug this in my calculator. Being very careful about the parentheses when dividing. And I get that it is 0.000004, which is 1, 2, 3, 4, 5, 6. 4 times 10 to the negative 6th. And the units of electric field are newtons per coulomb. And it is directed to the right. By the way, I'll explain why this makes sense in a second. Now, just like in the force example, if there are multiple source charges, and you're asked, compute the electric field here, all you do is you compute the electric field due to this guy, compute the electric field due to this guy, and all you have to do is do your standard right triangle thing to find the diagonal, which is the size of the electric field, and the angle of the electric field. I'm not going to go through this example in detail because you saw how long it took. But in principle, that's how you would do it. It's the exact same as the force calculation. Only difference is you only use the Q of the creator charges because there is no target charge. You're just asked about a place in space. All right. Oops. Now, here is something that's really interesting, and it'll explain why the units of electric field are what they are. Now, we had sort of alluded to this in the previous video, where we talked about if you place a positive test, so if you just have an electric field chilling here, you don't really know what's creating it, and you put a positive charge in, you can predict what direction the force will be just by knowing the definition of electric field as the direction a positive charge would be pushed. But the question might be, how hard is the push? Do you know how many newtons a charge will feel if it's put in a given electric field? And the answer is yes. And there's a formula which is really simple. The formula is just that the force a particle feels in an electric field is the charge of the experiencer, so whatever little guy you're popping in to float around in the electric field and see what happens, times the electric field in which he is immersed. So, for example, if I have an electric field of 10 newtons per coulomb, and I put in a proton, force would just be the charge of the experiencer, so 1.6 times 10 to the negative 19th, times the size of the electric field, which is 10. So this would be 1.6 times 10 to the negative 18th newtons. And of course, it would be directed along the direction of the electric field, right? The two arrows have an equal sign between them, meaning that they, in addition to having the same size, they both point in the same direction. Or sorry, not that they both have the same size. This arrow right here, which is a rescaling of E, has the same size as the force arrow, and that's what we just found. The size of the force arrow is this times this. And in addition, they share the same direction. So the force arrow, Q doesn't have direction, it just makes the E arrow bigger, but it still points in the same direction. So the F arrow and the E arrow both point in the same direction, and since the E arrow points to the right, the F arrow also points to the right. Now, one thing that's really interesting about this is if you instead put a negative charge in an electric field, we know from the last video that since negative charges they like being where positive charges hate being, or where positive charges hate being, you can view this as what charge might have been creating this electric field to get a rough idea. But anyway, we remember that negative charges get pushed in the opposite direction of where positive charges would get pushed. And that is actually automatically encoded into this equation, right? If we plug in negative, the force arrow is of size negative charge of the experiencer, so this time it's an electron, times the electric field. You get that it's negative 1.6 times 10 to the negative 18th, meaning that instead of being in the direction that E points, it's in the opposite of the direction that E points. Right? Because you have this negative sign here. Right? Sort of like how if you have a velocity of negative 2 meters per second, if you have a velocity of negative 2 meters per second, it means it's not pointed in the positive direction, it's pointed in the negative direction. Here, instead of, or here, a number like positive 2 E hat would point in the direction of E. A number like negative 1.6 E hat points in the direction opposite of E. So you actually have the direction, or the fact that negative charges get pushed in the opposite direction built into these equations. Now, just like before, it's a really, really, really good idea to look back after doing your computation and check if it makes sense, the direction. One final comment would be another way to approach this earlier problem would be to find the electric field due to these guys, Q1 and Q2, at this point, Q3. I should be using another color. Find the electric field here. You would have to find the electric field up and then the electric field to the right. In this case, they would point in the other directions. And then all you would do is multiply the diagonal electric field by the charge of the experiencer, Q3. Right? So there's two ways to approach this problem. You can instantly jump to the forces using Coulomb's law, or you can find the electric field at this point you're being asked about, and then multiply it by whatever charge is sitting there to find the force that that charge would feel. And this sort of makes sense because notice how E is missing the charge of the experiencer here, and then all you do to get force is you multiply by the charge of the experiencer. So really, this is just a restatement of Coulomb's law in terms of save multiplication by the experiencer for later, for whatever reason. Okay, last thing. Actually, one more comment here, because it's a very common test question. It'll be something like a CO2 molecule. So oxygen becomes negatively polarized. Or like if you have ions or things like that. Actually, CO2, I forget, my chemistry is escaping me. A question might be in things like groups of ions. Let's say you have this charge, and this charge. A question might be, find the net force on the middle charge. Okay? And again, we've already sort of covered this. You could already answer this from the video, but it's just a really common example that came to mind. The middle charge, your first question that you want to ask is, which direction is it getting pulled by each guy? So the negative charge is repelling it this way, and the positive charge is further attracting it this way. So you would compute the force from the negative charge, which would be a repulsion. You would compute the force from the positive charge, which is an attraction. Let's say you get answers of 20 and 10 newtons. And then since they're pointing in the same direction, you know that it makes sense to add them to get the total force. Conversely, if one of the creator charges was a positive as well, then in that case, instead of a repulsion between these two guys right here, there's an attraction on the middle charge. So if your answers were 20 and then 10 newtons but pointed in the opposite direction, you know that the net force is going to be 10 newtons to the right because these 10 newtons kill off half of this force. So that's just a reminder really to, before blindly adding sizes of numbers, check which directions the force arrows point in. That'll really clearly tell you if you should add, subtract, or if you'll need to do the Pythagorean theorem like we did above. It's just really tempting in these 1D examples to blindly add numbers, which can sometimes lead you astray. Okay, one last topic. Like I said, this will be a pretty quick video, is the formula for voltage. Oh, actually, one more comment here. I promised you I would explain what the units were on E, and they're newtons per coulomb. The reason this makes sense is you take the electric field, which is, let's say, 5 newtons of force per coulomb. You multiply it by how many coulombs of charge you have, let's say 2 coulombs, and your result is 10 newtons, right? There's 5 newtons per each coulomb of charge there. There's 2 coulombs, so the total force is 10. So this is really the equation you can go to if you need to remember what the heck are the units on the electric field. It's really just a force per unit charge. Similarly, voltage, it will also have a connection to potential energy per unit charge. So I'll write that. Actually, I'll write it in Galaxy Pen because it is pretty important. It's sort of inherited from how important potential energy is. And this will be reflected in an equation later, but it is really important. All right, the formula for voltage. Again, we earlier talked about voltage in the context of where do positive charges hate being. So positive charges hate being near other positive charges. So the voltage is huge here. And they love being near negative charges, so the voltage is super negative / really low. Here. Again, voltage just where positive charges hate being, that's places of high voltage. And the way you can compute it is that voltage is K times Q of the source divided by the distance. Not distance squared, just distance. Okay? Or I'll actually avoid inceptioning anything into your memory and just write not squared. Okay. As a quick example, I mean, this is really the exact same deal as the above two guys, just instead of using r squared, you use r. If you have a proton and a distance of 2 centimeters away, and you ask what's the voltage at this point, all you have to do is do Coulomb's constant times the source charge divided by the distance. Now remember, it's not the distance squared here. For voltage, it's just the distance. And I'm not even going to go through and cancel out these numbers. The units, though, I will say, are joules per coulomb, also called volts. Now, my earlier analogy of why is electric field's units newtons per coulomb? Why does that make sense? The answer was that there's this simple formula for relating the two. You take the newtons per coulomb, multiply by the number of coulombs, and that gives you the number of newtons. Here, it's the exact same deal. Voltage, all you have to do is, all you have to do to voltage is you multiply it by the charge of an experiencing object, and that will tell you the potential energy of the charge being in that place. Now again, the units on this, you have joules per coulomb, also known as a volt. Often when people will tell you things in terms of volts, but joules per coulomb is the useful one to check your units. Again, if you have 10 joules per coulomb of voltage times 3 coulombs, total there's 30 joules of energy cost for being there. Okay, so I will box this equation because actually I'll galaxy this one because you use this one quite often. In practice, this is really important because things such as batteries they're specified in terms of their voltages, and when you move charges across the voltage, what you're doing is you're injecting energy into them. Okay, that's how batteries work. They have a high voltage terminal and a low voltage terminal, and this is really just for your guys' benefit. What happens is that, by the way, circuits are pretty confusing. You pretend that positive charges move to avoid negative signs, but what is the standard story of what's happening is positive charges are being charged up by the battery. They're going from here to here, so they're being moved from a place where they loved being. They rolled all the way down the hill to get there, and they're being lifted up by the energy in the battery. They're consuming the energy in the battery to get up to a place where they hate being. That's the equivalent of pushing a bowling ball up a hill to put it in a place where it hates being. And then they traverse the circuit. Their energy is eaten up as they roll down the hill by other components of the circuit. Let's say you can use them to fight your way through resistors. And then you return back to the place where you love being, the equivalent of the bowling ball having rolled down the hill, powered your generator, and now it's finally where it wants to go. So anyway, batteries are a place where voltage is used to specify how much energy is being outputted. So that's why this equation comes up so often. Okay, last comment before we wrap up the video is sometimes problems will involve things such as this. They'll give you a 3-charge setup, and they'll ask, what was the total energy required to form this system? Okay, actually, I realized I want to do a quick example of voltage just because it's so common, and it's important to know how to do it in practice. So a quick example would be an electron is moved from a place with V equals 0 to a place where V equals 2 volts. Actually, this will be a really useful example. I might even edit the video to have this first. Oops, to a place where V equals 2 volts. First question will be, did energy have to be put in? Like, did energy have to be inputted for this to happen, or would it naturally happen? Is this the natural, favorable thing that would happen? Okay, you're moving from a place with V equals 0 to a place with V equals 2 volts. Now, a positive charge would hate being brought in that direction, right? It likes being near the lower voltage. It hates being near the higher voltage. That means the electron loves having that happen to it. So this is an energy favorable process. Okay. Now let's actually, for part B, I'm going to move this example down. Part B will be, what's the size of the energy release? Okay, all you have to do there is do that the potential energy change would be Q times, and technically this is like delta V and the change in potential energy. People often write this implicitly. So actually I will go up here and I will edit our equation to have these deltas. Usually you talk about things being brought from one potential to another potential. Sorry, I shouldn't say potential. From one voltage to another voltage. And in the process, some energy change happens, whether it be a release or an absorption of energy to make it happen. So the size of the potential energy release will be the electron charge times, sorry, so this is negative, times the delta V, which is V final 2 minus V initial 0. So the delta PE is negative 3.2 times 10 to the negative 19th. And a negative change in PE, sort of like how a bowling ball rolling down a hill gets to a lower PE by the end, negative PE change is favorable, right? Again, if you have a bowling ball, it starts up high on a hill, it rolls down a hill, the change in potential energy over that is negative, and the bowling ball loves it. It's what naturally wants to happen. Here we have the same thing. The change in potential energy for the electron is negative. It's gone from a place where it hates being, where it had high potential energy, and gone down to a place where it's comparatively lower potential energy. This will happen all the time. This is how you figure out how much energy a battery or an electron has after it goes through a battery, for instance. And a final comment is that 1.6 times 10 to the negative 19th joules of energy, and I'll underline energy in Galaxy Pen, is called 1 electron-volt. This is not volts. It's not 1.6 times 10 to the negative 19th volts. It is a unit of energy, and it's equivalent to how much energy you get if you move 1 electron of charge through 1 volt of voltage difference, right? That's how much potential energy happens when you move 1 electron through 1 volt. So just a super galaxy reminder, because people forget this all the time, so much so that professors even ask it as test questions. Is electron volt a unit of energy or what? And people always answer something else, but it is a unit of energy, okay? Electron volt is a unit of energy. It's a very small unit of energy. Okay, now I'll finally go back to this example that I mentioned earlier. There is one final type of problem, which is what was the energy required to assemble this system? Now, at first, you would say, oh, I need to compute the voltage due to this guy on this guy, and the voltage due to this guy on this guy, and then sort of do that for all the combinations and add them up. Okay? Actually, I'm going to simplify this problem. Let's just say we have 2 charges, a positive and another positive. And the question is, what's the energy required to form this system? So your intuition might be, find the voltage due to this guy here, and then multiply it by the charge of this guy to get how much energy cost it took him. And then at the same time, compute the energy cost that it took to bring this guy next to this guy by doing all those steps with the 2 guys interchanged. Now, the issue with that is that you've double counted. And this can be a little tricky, so do your best to follow along here. When you're forming a system, you start off with one guy in isolation. It didn't cost anything to have him brought there. Later, you, from really far away, you bring in his buddy, and that does cost things. As you're pushing him this distance, he is having a repulsive force applied to him the whole way. So he's being pushed up a hill the whole way, and that force times distance is the work that it took to bring him there. So really, you should only be counting his potential times charge. And again, that's because it didn't cost anything to bring this guy here in the first place. It's not like there was already a pre-existing electric field from this guy's ghost. It didn't work like that. So you've actually double counted, and all you have to do is divide by 2 if you want to do the problem that way. So, And by the way, it might seem stupid to intentionally double count. Like, why wouldn't you just do the simple calculation and call it a day? And the answer is that when there's more than 2 charges, so when there's 3 or more, it's tough to keep track of the pairs. So people just tend to do it for every charge. They compute the voltage at every charge's home, multiply it by the charge of the inhabitant, and they do that for every charge, and they know that they've counted every pairwise force combination twice, so they just divide by 2. So often this is written on your equation sheet as work total is 1/2 the sum of each inhabitant times the voltage at the inhabitant due to the other charge. And this is added over all charges. Okay, so this formula, you don't use it too often, but this does appear on equation sheets. With this funky 1/2, so that was just my shot at explaining why there's a 1/2 there. And again, it's only for this very specific scenario of this very restricted question: what was the energy required to assemble this system into its current state? Okay, what was the energy required to build this charge configuration, starting with them all far away and slowly bring them in towards one another? Okay, again, you won't use it nearly as often as the other 4, but I did want to explain sometimes people start putting this 1/2 in the voltage equations, which leads them to problems in the 98% of problems that you actually do. So that's why I go over this 2% of problems formula, just so you only put the 1/2 in this very specific scenario. Otherwise, do not worry about the 1/2. Don't get tempted to put it in places it shouldn't. All right, guys, that is about it. Now, of course, there's a lot of possible examples in this subject, and I can't cover all of them, but hopefully this was enough to at least get you to hang on with like the main concepts and to be able to approach all those more difficult problems. But don't hesitate. If there's a difficult problem, let me know in the comments, because this is a really important part of Physics 2, and I can do my best to put out example-specific videos or to put out additional information if there's problem types that are really common. All right, guys, good work. Excellent job making it through electric field. This is a really tough subject, so head high. All right, guys, I will see you in the next one.